What I also want to delve into is when we have, as engineers, the traditional methods, like let's say we use OpenFOAM for CFD, we have this kind of convergence criteria. Does this also exist in the SPH method, or what criteria do you use to tell if the solution, if we approach the right solution? What would you say here?
So what I need to emphasize is that we always compute transient flows.
Mm-hmm.
So
Okay.
there's no steady flow. So and so then I think the convergent criterion question shifts a bit. Yeah. In contrast to other SPH solvers out there, we have an implicit formulation which like really solves for the Navier-Stokes equation.
Mm-hmm.
And in this formulation, there's a convergent criterion for every time step, of course, that tells the solver, yeah, okay, we met the criterion, which is like compression. So it's we can say, okay, that the volume does not compress, which is important for fluids, and this is in there, and this makes also our solution so much more robust than what is usually known as SPH solvers.
Mm-hmm. Jens, do you want to add anything here?
Exactly. So this was one thing we learned when we got in contact with the mechanical engineers. They told us, for example, they have an application which is a gearbox simulation, so sloshing of oil in a gearbox. And using Eulerian approaches, they encountered the problem that they initialize a specific amount of fluid, so specific volumes like 400 milliliters, for example. And throughout the physical time they're computing in this transient setup, they lose volume due to the numerical diffusion. And so what we learned is at this point that with a particle-based approach, solving for the compression, as Marcus just said, we can ensure that no volume is lost throughout the physical time that is computed. And yeah, so this is an example where you can actually visually also see the result of the solver and the residual, which is the compression of the system which is solved.